Javian, and I chose my project on rocket nozzles. Alright, so basics of Rocketry 101. So rockets work off the principle of momentum and Newton's third law. So in order to produce a large amount of thrust, the rocket needs to shed off a lot of mass at a high velocity. And if you guys remember from my last presentation, the easiest way to do this is with combustion. So looking at the diagram below, you see the high velocity combustion gases go one way, and hopefully point the rocket in the right direction because the rocket would go the other way. So what are the basics of a rocket engine? There's two main sections, the actual combustion chamber and the nozzle itself. I'm focusing on the nozzle, and there's three sections of the nozzle, which is that diverging section, the throat, and the converging section. So why are nozzles necessary? Basically, they direct the gases and accelerate them as fast and as efficiently as possible. So it works off the Venturi effect. So with a constant mass flow, decreasing area actually increases the fluid velocity. The area decreases up until the gases reach Mach 1, and a critical property happens if the surrounding pressure outside of the nozzle is significantly less than the chamber pressure. What would happen is the gases would actually accelerate even faster than the speed of sound, so you get a lot more thrust that way. So nozzle requirements. So you actually get a more powerful engine with higher pressures and temperatures reached inside the combustion chamber itself. Uh, the temperatures could actually reach 3,000 degrees plus in temperature. So therefore, our nozzles need to withstand high temperatures and pressures as well as being lightweight. There's one major problem. There's few materials, if any, that can withstand the extreme temperatures. So in order to kind of select the material choice, I have to model as a heat exchanger because there have to be some sort of cooling method in place to make sure the material doesn't melt. So design requirements, we have the length and radius and chamber pressure are specified. Obviously, the material must be non-flammable. The objective is to minimize the mass and cost and to maximize the heat flow per unit mass for this nozzle. And we're trying to pick the right material choice and the wall thickness itself. So we have some basic equations. This is straight from the textbook. Heat flux through heat exchanger wall is given by that equation there. That equation by itself won't be enough to select the material choices. So I also modeled it as a pressure vessel as well. So thin wall pressure vessels fail mainly due to hoop stress, which is found through that equation. The nozzle will cycle through being pressurized and unpressurized, so cracks will form. So the stress that would cause the cracks to propagate uncontrollably is given by that equation. And since the thickness is small compared to the radius, we could estimate the nozzle volume of the material equal to that. So we don't want the nozzle to leak before breaking, since we're modeling as a large pressure vessel. We also don't want the nozzle to unexpectedly burst, so we have to have the hoop stress has to be less than the yield stress, it has to be less than the fracture stress, obviously. So here's some derivations, exactly the same from last time. This basically just finds the relation between the four material indices. The first one being the heat flux. So there's the equation that's straight from the notes as well that allows us to maximize the heat flux by finding the largest constant of yield stress times the thermal conductivity. We also could minimize the mass by finding the largest strength to density ratio, and we could also maximize the crack length by finding the largest fraction toughness to yield stress. And lastly, the last thing to kind of like narrow things down is cost per kilogram, since we only care about mass. All right, so here's the first chart itself. This is the yield strength to thermal conductivity. This allows us to find the material that would conduct the most heat away from the combustion. And we see we're kind of playing with four materials. Copper alloys and tungsten alloys are really the top two that I'm considering really, but we also have aluminum nitride and silicon carbide. Next up is the strength and density ratio. Like the last chart below, or like the last chart, we have the values there. Same thing here, we have the values to the right. We can see that silicon carbide is very good compared to tungsten and copper alloys. Aluminum nitride is actually not on this chart, so there's no value for it. So it's going to be removed from consideration. Same thing with the fracture toughness to the strength. We can see that copper alloys come on top by a significant margin, and the tungsten and the silicon carbide are really way below the copper alloys. And lastly, the last material index, we have all of the materials and their cost per kilogram. You can see that again, copper alloys comes on top. And to kind of consider the embodied energy, I took this straight from the notes as well. And again, copper alloys come on top, so it's kind of clear what's the best material choice for our rocket nozzle. So this is all the values put into one chart. All I did was rank them from first to last. And the idea is that if you come on top, you have the least amount of points. And it's very obvious that copper alloys is the best choice material for this application. All right, so sweet. We have a rocket nozzle material. So now we need to manufacture it to actually make a nozzle. One major problem is that rocket engine design and manufacturing is a closely guarded trade secret. So we kind of need to work backwards, kind of with the information out there. A cool thing is that there's a company called Launcher who made entirely 3D printed rocket engines made from copper alloys. So I'm going to start there. So if we're using copper alloys, it's a non-ferrous material, and if they're 3D printing, it has to be some sort of powder method itself. So we could see that powder methods and non-ferrous metals are compatible. We could also see that the shape will be circular, and powder methods also work with that shape, so that checks out. Since we're using powdered methods, we have, looking at the mass charts, we could see that the engine itself has to be very lightweight. So that kind of limits our size by a lot. With the joining methods, we're really talking mainly about welding and fasteners, but fasteners have been eliminated just because it requires extra material to seal up properly. So welding is definitely going to be the way to go. But since it's also 3D printed, we also don't really have to worry about joining methods since it's already joined when it's printed out. Looking at the section thickness, we could see that the nozzle could be 1 millimeter to 10 millimeters thick, which is pretty reasonable, I think. Going on to tolerance and roughness, we can see that powder methods do not have a very good tolerance at all. Standard tolerance of 0.1 millimeters, which is plus or minus 5 thou, is pretty standard. So we have to do some precision machining in order to make sure it's within tolerance. Looking at the roughness, powder methods are also very rough, so we also have to do some sort of precision machining or other method to bring down the roughness as needed. And looking at economic batch size, we can see that powder methods are really meant for a large batch size, which for Launcher itself makes sense because their idea is that they're trying to churn out thousands of these engines for space applications. So with that in mind, we chose the material as copper alloys. Based on what I found online with Launcher, the process has to be powder methods, and the finishing has to be precision machining to tie in the tolerance and roughness, and the joining method is welding or with the 3D printing methods as well. So working backwards, this is kind of what we came up with. So looking at the actual manufacturing process of Launcher, they're very gracious enough to provide lots of pictures. So this is actually it being just finished 3D printing at a metal 3D printer. You can see all the copper dust is left over. After they remove the material or remove the nozzle from the machine, they put it into a sintering oven to actually harden the material itself, and they machine it down to tighten up the tolerances. And you can see that the nozzle is super small, so the mass makes sense for the powder methods. And looking at the arrows, you can see how they actually cool down the nozzle. They actually have an entrance for the fuel to come in, snake around the walls, and meet up with the oxidizer to actually start the combustion process itself. which I think is super awesome. And yeah, so here's my work cited, and I'm gonna play like maybe 5 to 10 seconds of the actual launch video or the test fire itself if it wants to load. Oh, well, that's not super important. I'll put the video in the chat, but that's my presentation.
Thank you.